Okay, so this is our process control and dynamics final project.
I'm Jason.
Taylor, Tanner. And so this is our project. So you can see over here that we've been using the same TCLab that we've been using for the whole semester. So it's got 2 heaters as well as 2 temperature sensors on there. And then we've also decided to help implement a fan in order to get better temperature control. And so here we have our power supply right here, and then we have and that's putting out 5 volts, and then we have this little guy right here that helps us control the fan via pulse width modulation.
So let's talk about the modifications that we made to the traditional PID controller, normally used to control the TCLab. The first thing of note is that we eliminated the derivative term now. The way that this controller works the fan is if the process variable is, or if the temperature is 1 degree higher than the set point, the fan will turn on to 100%. If the set point and the process variable have a difference of between 1 and 5 degrees, then the fan will turn on to 50%. We've calibrated the fan so that the value of 1 corresponds to 50% on the actual hardware. So now let's run this controller and see what it does for the fan. At 10 seconds, we should see our first set point change up to 40 degrees. Right there.
The heater is now on, like Taylor mentioned, and the process variable is now approaching the set point. So as you can see, our process variable is reaching the set point of 40 degrees quite quickly. So we're now going to pan to our fan. And our fan has started and stopped and started. And so here we have a set point change highlighted in blue that went down to 35 degrees. And as you can see, the fan is on to 100% and is cooling the TCLab more effectively than would have been done before. One important note to mention is that the fan is reducing our overshoot. The reason this happens is because, like we mentioned earlier, as the process variable is getting larger than the set point, the fan is kicking on and cooling it down quicker than would happen normally. So because of that, there will not necessarily be a peak when we look at our graph because the overshoot will have been eliminated by the fan. The pattern we've seen of changing the set point higher or lower and the fan being activated either to cool down to the set point or to cool once the set point has been exceeded will continue as the run.
So in this run, we use kind of what you may call an if controller. So it said that if we were above the set point by a certain value, then turn the fan on this much. If we exceed that value and go into a different range, then turn the fan on even more. But we also had used the idea of creating a P controller for the fan, where the various responses and using the kind of if controller versus a P controller, we'll pass it off to Taylor so he can talk about some of these differences in graphs.
Okay, so the first thing we're going to look at is what would have happened had we used a normal PID controller. This was the response for a normal PID controller. You can see it overshoots by a significant amount, and then when there's a drop in the set point, it takes a long time to reach it. And we see the same thing here. It overshoots a little bit too much, never really settles at the value, and then takes a long time to reach the set point when it drops. Here's the controller that we just showed. You can see it gets to the set point, and because the fan kicks on when it starts to get too hot and overshoot, it levels off right there at the set point. When you have a set point drop, it drops and quickly settles at that lower value. When it rises, you can see again, we eliminate the overshoot, settle at the value, and then we drop and settle at that value again. The integral error for the PID controller is 3,552, and the integral or absolute error for the if controller is 2,398. We also tested using a P controller for the fan, but found that this didn't work as well as just the normal if controller. For this, we used a K value for the fan determined from step tests. you can see that the fan, instead of just oscillating between 50 and 100, oscillated between values, oscillated between several different values. Unfortunately, this one had a little bit harder time maintaining itself at the set point, and as can be seen here, it also prevented the controller from properly reaching the set point. And so the integral absolute error was greater for this controller than it was for the normal if controller. Because of that, we concluded that the if controller was the best way to maintain the temperature set point for our TCLab and fan configuration.